additional examples for statics in ME401. I wanted to create a couple videos for some of these. This is out of a problem out of the Miriam workbook. Miriam and Craig was the statics book I used in undergrad, and they had made this workbook that went along with it. So I thought this was I kind of liked this problem. So this is like an aircraft landing gear, and it's being raised by this 4-bar where there's a torque being applied right here, and going through this 0.8 meter link right here. So this is like the crank. Here's a 0.8 meter coupler, and then we have the rocker would be this 1 meter length right here link, and then the ground is like 0.6. There's this air resistance that's acting right here on this wheel as it's coming down. That's got 100 newtons right there. We also want to include maybe the mass, which the mass center we're told is right here, and all the other masses are neglected. So we want to find the torque right here that's required to raise the gear at a constant velocity to position shown. The forces on each of the pin and the mechanical advantage. I always think of this mechanical advantage right here. I don't know. I think in this case right here, this force is trying to make that thing go back up right there. So that makes it kind of, we could say that that's this is actually helping it close right here. So I don't know. I think it may be, I would actually make it just based on this weight right here. I think I would like leave out that force that's right here, because that's not really telling us a true mechanical advantage right here. But anyway, the thing that we want to do is make a free body diagram of these parts and these pieces as we're going through here. And so we know all the loads right on here, so we could find out what that force is going to be by taking, and we're going to take the sum of the moments about A in order to figure out what that force is. So I think I have a ruler right here, and I will try to make a good sketch of this piece and put all of the forces and loads that are onto this thing. So I'm going to put the wheel in here as well. This looks to me, it almost looks like it's going to be a 90 to this, but you can't really tell that that's going to be a 90 for sure. I mean, so sometimes you have to be careful and work through and make sure that that is double check whether it is a 90 degree or not. So what we find right here, what we can see from this is that this is 0.8 and this is 0.8. And then if we also do the geometry right here with the 0.6 and this right here, we'd find out that this is 0.8 as well. So we find out that this is an equilateral triangle and that is 60 degrees right there. So we had to do a little bit of geometry and double check. And then we can also find what this beta is going to be. That beta right there, well, that's a 3, 4, 5 triangle for one thing, so we could actually we might even have memorized that, but we could also find that that beta is going to be well, I'll use the sine right here, right? Well, maybe from this, because we have the opposite in this, so we'll take the 1 meter, no, sorry, I'll take the inverse sine. That's what I'll do. Inverse sine of 0.6 over 1, right? That's going to be the opposite over the hypotenuse, or 0.6, and then take the inverse sine, and we get this is 36.87 degrees. So this right here is not 90, but it's pretty close, 96.87. So that's something you got to be pretty careful about when you're doing a problem, is to try to see. Now, I might want to exaggerate and make it not look like, it's like right here would be 90, so I'm going to kind of exaggerate and maybe, you know, I'll make this like that right there. That right there is going to be the line of action for this. And this guy right here is a two-force member between D and C. So that's some of the reason why I want to get that angle. We don't know this guy right up here, this reaction, so I'm going to assume he's going to be in the positive right there, and we'll figure out what those are going to be in a minute. So that right there. We have this guy, and it's kind of unfortunate everything is kind of clogged together right here, but let's put him down over here and say that he is going to be the weight of that whole assembly, and here's where this force is going to be applied right here of 100 newtons. Okay, so we have 100 newtons acting right there. So we have to do, for this, we have to do the sum of the moments that are acting about A in order to find, this is the force that we're going to try to find as part of that. And so I'm going to break this one up into two. I'm going to assume that this is going to go this way right here, that this thing is pushing in here. I think I'm going to find that I get the opposite. Is that true? Right in here? I think so. I think it would actually be pointing in the other way. But we don't quite know, because this one is trying to make this go clockwise, whereas this one's trying to make it go counterclockwise. So is this force right here going to be going this way, or is it going to be going that way? I drew it as being going this way, just as my assumption. So that's the force of the D in the X and force in the D in the Y, and that we know that the force of the D in the Y is going to be FD, and let me see if I'm going to get this correct right here. Yeah, that's going to be 60 degrees, so that's 60 degrees right here, right? So that's going to be the cosine of 60. Did I say that right? FD is going to be the cosine of 60, yeah, and FDX is FD sine of 60. Just writing it over to the side right there. So when we go to put these in there, we'll use those. And then other things I might want to get, I need to get some distances as part of this right here. So the distance right here, from here to this position right there, is going to be, that's a little bit of a pain. First off, this angle, remember, is going to be the same angle as right here, right? So that's going to be right in there. That's going to be that beta. And so I know this one, so it's going to be 1 meter plus 0.2. Man, this is a pain right here, right? Because yeah. Okay, so we're going to say this is, it doesn't quite look like it's in line, but let's say that it is in line. It was just drawn poorly, right? I think that's right, yeah. All right, so we're going to have 1.4 is going to be this right here. So it's 1.4 times the cosine of my 36.87. Right, so maybe did I do that? Well, we gotta be careful here. I see my, okay, yeah. We also want to have this distance right here. Okay, so this distance is also something, and I'm not putting it in a very good spot right here, but we want to have this distance for this guy right here, and then that's gonna, and then of course I put that in a bad spot for this distance that I want as part of this. Okay, so I want to have this distance right in there, and I also want to have this distance right in here. All right, so I have my dimension lines crossing. That's kind of messed up, but hopefully that won't be too difficult to figure out. Yeah, it is kind of difficult to figure out from all of this. Let's see. Other things I want when I have is 75 kilograms. So this is going to be 75 times 9.81. So let me figure out some of the in-between numbers right here. 75, 9.81 times. So this is our 735.8, 735.8, right? Newtons. So that's definitely going to be the one that's going to be going influencing the thing to go clockwise, whereas this is only 100 newtons and it wants to go counterclockwise. So this is probably a pretty good bet that we made up here, that this is going to try to go counterclockwise. So let's see, this distance right here, 1.4 times that 36.87, and some people would probably do the ratio, like to do like the 4/5 or whatever onto this, but I went ahead and did it this way. So I got like 1.120 is what that's going to equal right here, and this distance right to here is just going to be 1 meter right here. So we actually have that distance. Whoops, we have that 0.6. Yep, that 0.6 is actually going to be the distance for the vertical one, and then this one is going to be 0.8. Okay, so I think the only one left to do is going to be where this weight is located. So that's going to be 1.2 times the so that's going to be the sine, yeah, because so that's, if that would come down all the way to there, that would be like this distance right in there to be able to come in there. So I think I can write that onto the side. All right, so let's march through here, and let me start out with the ones I don't know. So I'm going to take this FD. Let's take the FDY, and that's going counterclockwise. So FD times the cosine of 60, and that's going to be, and it's positive because it's counterclockwise, and multiplied by this distance, which we know to be 0.6. Okay, and then I'm going to go this one right here. This is also counterclockwise. So FD times the sine of 60 right there. And that one, its distance is going to be the 0.8 that we came out with, that we decided because of that 3, 4, 5 triangle. Okay, so those two are taken care of. Let's take care of the weight, right? So now we have the weight, and the weight is going clockwise. So we get a negative 735.8, and that's going to be that 1.2, right? Because it gets to 1.2. And we're going to use the sine, so it's going to be 1.2 times the sine of our 36.87 right here. And then where are we at? This guy, he's going clockwise. He's a helper, counterclockwise. He's a helper, and that distance, that was the 1.12. And I think I got all of them. So now we find that unknown, that FD, as part of this. So got these. Okay, so I'm gonna let me take my 730, this guy, and go 1.2 times him, and then the 36.87 sine, so it should be like 0.6. And then I multiply right there. Okay, and that's going to be negative, so it's going to come over onto the other side. I'm going to add, so I'll make it negative for now. I'll go 100 and then 1.12 times it, but we're adding that to there, right? So that removes some from here, and but I'm going to make it's going to jump over to the other side. Now I'm going to divide that through by these two things added to get, and then, okay, so let's see, is that problem really going this long? Is this really taking that long? Wow, it already went 15 minutes. Wow, I didn't realize that time was flying right here as I was talking my way through this problem. I don't think I'm just going to listen to this, but that's okay. I said I was going to do it, so I'm doing it anyway. It's the contractual obligation. 60 sine and 0.8 times, and we're going to add those through. And let's hope, let's divide. We get the same number, 420.8. That's what I got previously, having done it a different way. Some differences in the not a different way, but I went through different angles and that kind of thing. So if we want to try to find what the forces are in the x direction, let's go ahead and break that down into FD x is going to be that 420.8 times the sine of 60. Right, and that's going to help us a little bit here. Let's see. Maybe not sine of 60. Okay, so that's going to be 364.4 newtons. F d y 420.8 cosine of 60. So that's just going to be 1/2 of the thing, isn't it? So 60 cosine, yeah. So it's just 210.4 newtons. Okay. So we take the sum of the forces in the x direction and y direction, and that's going to give us what that pin, since we were asked for the forces in the pin. So sum of the forces in the, let me zoom out because I keep landing off of the page on here. Sum of the forces in the x direction equals 0 off of that free body diagram. And so I showed that as a positive up here, so let's keep that in there. We also have the 100 newtons is positive, and we see that this right here is 364.4. That's all positive. I don't see anybody else. So we obviously chose the wrong direction as that. We add 100 to it. We could do that in our heads, and we get negative 464.4 pounds. So obviously 464.4 pounds going the other direction, right in there. And some of the forces in the y direction. So let's see, I chose as a default upwards. And let's see, we have 735.8 going downwards. Let me put that negative. He's down, right? So negative. And then this guy was going upwards. What? I said 710. Let this come in. Okay. 210.4. So we have FAY, and that's going to be 735.8. All right, so I'm going to get a 525.4 pounds, and I chose correctly, right, that it was going upwards. So, you know, what we would probably care about, though, is the magnitude of that, because we're looking at these forces on this pin. We'd want to know what the bearing forces were going to be, right? I'm saying it's on a pin right here. We're saying a pin, but it would really be a bearing, right? That would be onto the thing, and we want to size that bearing. So we would want to know that FA was the square root of the 464.4 squared and the 525.4 squared. So I get 700 and 1.2 pounds. I just wrote pounds in a couple of places, didn't I? Newtons. Don't get your units confused. All right. And it didn't really matter what direction that was going in. We really only care about the magnitude here. Now, the main thing that we cared about in here was trying to figure out what this moment was going to be, right? So we have this guy right here. That right there is all that is one of the things that we wanted to know. Here's another thing that we wanted to know. So let's find this last, find out what this moment is going to be by drawing a free body diagram, and I'll bring that down to here so I can get some amount of accuracy in my angle right here. And we also have this thing is coming down, and all right. So, by the way, maybe it's going to be better for us to draw as a side little view right here, the free body diagram of our two-force member. Here's our FBD of that two-force member right on here. So if this is coming up this way, that means that this thing is in tension, right? It is pulling on there. So in this direction, it's pulling in there, right? There's going to be our FD. And in this direction, it's also pulling here, right? So there's FC. So in this. So in this direction down here, this is our FC right here, right? That's an important thing that we want to try to include in here. So we know we're going to have, in terms of forces, the reaction forces at B, we're going to have FBY coming up that way. And we're going to have, FBX is going to be in this direction too, right? FBX. And simply because we know that the sum of the forces are going to have, we actually kind of know that the direction of this needs to come back up in that direction, right? That the X's need to balance out and the Y's need to balance out. There's nothing else right there. But there's also going to be, if that thing is trying to go clockwise, this guy better go counterclockwise. So here is the moment at B that we need to apply right there. And let's declare that this is an FBD. We really should say what the X and the Y are going to be, even though that's not going to change into this. So what I decided to do for this one right here, let's see. I'm looking at my own work. Okay, so this right here, and looking at it back up onto here, recognize that this is going to be 30 degrees and 30 degrees right in here. So the angle that's formed right in here is 30 degrees and 30 degrees right in here. And this length of this thing is 0.8, right? So we take the sum of the moments about B, and this is not that. This is like all of the moments that are B, but this is like a specific moment. It's well, not the reaction moment, but it's the applied moment that's going to be put onto here in order to lift up this whole piece right there, right? So, and we show it's counterclockwise. So I'm going to say it's MB as drawn right there, and then this is the only force on there that's going to, these forces are eliminated because we're taking it about B. So we have that FC that's applied there that we know is 420.8 newtons right there, and the arm it's okay. So what I would do is I would only take the one that's going to be the sine of 60 right there. So it's only the stuff that's coming in the perpendicular direction right here. So this angle right here is 60. So I only want to go the opposite, the opposite from that angle degree right there. So I said 60. And now the arm is 0.8 right there. So what I've done is, and the choice that I have quite often is to figure out the geometry for the distance or I can take the components. I could either adjust the distance so that it's the perpendicular distance, or I can adjust the force so it's only the force that's going to be perpendicular to the distance that I know. So I decided to adjust the force, so I'm only going to have the component that's perpendicular right here. So that's what I did. And on my original sheet, I did the other way around. So the moment that I'm going to get right here is just going to be that 420 times sine of 60 times 0.8, and I get that it's going to be 291.5 Newton meters, and it's a counterclockwise, so maybe I'll make that a moment vector right there. That's going to be the answer. And here is, so I think I got all the pins except that, okay, and by the way, the pin at B is going to equal the pin at C, and you could see why, because there's only one force acting here at C, so this has to be equal and opposite to it. It just has to be. All right, so we also know that the this right here is what happens at C, which is also what happens at B. All right. Cheating by writing that out. And then lastly, we want to get the mechanical advantage. All right. So here is we want the torque. Right. We want to figure out what is the torque at on AD that's happening right here. What is the torque on this thing right here compared to this right here? So this guy is overcoming all the torque that's happening onto there, right? So I would say, so this is like the torque in that's being applied, and this is the torque out right here. So the T out, if you will, if I was just going to put this onto here, right? I would say it's the 100 newtons times the times the distance right here, right? And then minus this. Well, no, I did go the other way right here. Here it is right here. I would say that the torque out was going to be that 735.8 right here times my what was my distance that this one was? This was the 1.2, right? Times my sine of 36.87 right there, and then but it's going to be minus, right, because this was a helping one, so that was the 100 newtons times my 1.12. So this is what I would consider the quote-unquote torque out of this thing. I would say, I didn't do that. Okay, so 735.8 times my 1.2 times my 36.87 sine. Of course, I could just put 0.6. So I get that's 529.8, that part, and I'm going to subtract out 101.12 times there and subtract that out. So I say that it's 417.8 Newton meters was what I have. So if I said that there was a mechanical advantage right here, I would say that it's torque out divided by torque in. So the torque out was 417.8 and the torque in was 291.5. So I guess I'll just divide it. 291.5. So I have a mechanical advantage of 1.433. That's just this conceptually, right? Something that we want to check to try to see how, the effectiveness of the arrangement of the linkages to see what kind of advantage or disadvantage we might have because of that arrangement. And I think it's specific to the position also that it happens to be in. So if it changes in the angles of the thing, it's probably going to have a different mechanical advantage. and we can all know how that's like related to the transmission angle. So this was a 30-minute demo, so maybe it was too long. I don't know. I don't know how useful it'll be, but it is now recorded.